Here we have today's exercise. Let's put it out here where you can see it. This, of course, is the key, but your student version looks just like it, except without the red lettering. And there's a considerable amount of information here that's designed to help you understand the procedure. There is also an extra video that you should watch before you maybe even before you submit your lab notebook pages for approval, so that you can watch the main video. It gives you a discussion of the theory, and you'll recognize some of this information that is in the video discussion. So I'm not going to labor that one right now, because there's a complete video describing it. What I will do is go to these discussion questions, which are there for the instructor to give to the students, and this may also be in the pre-lab video, but I'm going to put them in this one just in case, to be sure that we don't miss them. And then when you prepare your lab notebook and video the pages so that I can grade them and open up the demonstration video for you, you'll need these pre-lab questions. So you'll have to answer those in your lab notebook. And then here's the rest of the method that goes with it. And there are some lab questions. Consider these post-lab questions right here. These post-lab questions you won't have to have in the initial prep of your lab notebook, but you will have to put them in your report. Okay. So let's take a look at these discussion questions, and the reason I'm going to take time to do these now also is because I'm waiting for my pH meter to stabilize. Okay. I'll discuss all this equipment later, but for now, you will have it, by the time you do this lab, you will have had defined for you what pH means. And pH is a measure of acidity. Actually, it's the negative log of the concentration of hydrogen ions in solution. Right? So we can start off with, oops, excuse me, need something to write with. Okay. I've got everything set up here to receive the data, so I'm going to try to stay on this side of the board as to not leave any background information there that's erased and smudged. So the first question in this discussion questions is define the following terms. And the C and the D, you only need to provide the formulas for it. Okay. Equivalence point. What is the equivalence point? Okay. The equivalence point is equal to the point in the titration, and that's what we're doing here. We're titrating, we're adding base in small increments to a known amount, a measured amount of acid. The acid is acetic acid. The base is sodium hydroxide. So we're adding this to a known amount of that, and we're watching the change in pH. And at a certain point, the equivalence point, the amount of acid equals the amount of base. And that's the equivalence point. But what we mean here by this is general terms. Exact terms are the number of moles of hydrogen ions equals the number of moles of hydroxyl ions. Okay? Notice in this particular acid-base reaction, You have hydroxyls coming from this one, hydrogen ions coming from that one, and when they're equal, that's the equivalence point. So B is the end point. B is related to the equivalence point, but they're not exactly equal. All that's required for the end point is to have some sort of indicator, usually a color change. And we generally use, in this class, an indicator called phenolphthalein. And when the color changes, it's very close to the point at which the hydrogen ions equal the hydroxyl ions. But the end point is usually not exactly there. The end point is the position in the reaction where you're close to the equivalence point. Okay, what is the Ka? The Ka is the equilibrium constant for the acid neutralization reaction, right? So when we conduct this reaction, we can write an equilibrium expression for that. Well, as it turns out, this and this and this are all spectators. All right? So the Ka for that, well, I should say, let me write it this way. The Ka is the equilibrium constant for that reaction. And the Ka will vary depending on the this part of the reaction. Right? This is sodium hydroxide is a strong base. The weak acid determines the Ka. That's the equilibrium constant. And it can be written in terms of this reaction. Right? So this is going to be virtually undissociated, just very slightly dissociated. So what you're going to have is this would be considered a spectator, but since this ion is not dissociated up here, these can't be canceled out, so I shouldn't say that. Those can't be canceled, but the sodium can. So what we get is an equilibrium constant, Ka, that's equal to this and of course water isn't included. Remember, because with equilibrium expressions, pure liquids are not included in the expression. Pure compounds, pure elements, they're not included. So it would be this one divided by this one. There you go. Oh, and the hydroxyl, because this is completely dissociated. Pardon me. There you go. So that's the expression for the Ka. And this is unique to this weak acid. All right? So the last one is, what is the pKa? Well, you remember in our discussion, or in the discussion that precedes this lab, the P prefix is purely a mathematical construct. pH is defined as the negative log of the hydrogen ion concentrations in solution. So pKa is the negative log of the Ka. Right? So all you have to do is take the negative log of that value and you get the pKa. So that's Discussion question number 1. Now, why am I doing all this? Because when we get the data from this experiment, we're going to graph it, and I'll show you where that graph is. Here's an example of the graph. Let's see, where is it? Oops. There it is. This will be the volume of base that's added, and this will be the pH in response to that addition. And by watching that other video, the pre-lab video, I will explain in that video where you find the pKa on this graph. And once you find the pKa, you can solve this for the Ka. And that's the objective of the experiment, to locate and determine the Ka for acetic acid. And you do that by graphing your data and querying the graph for the Ka, the pKa. All right? So let's move ahead with number 2. All right, question number 2. If 39.3 milliliters of sodium hydroxide, 23.9 milliliters of sodium hydroxide, and I assume this is, yes, the question is, what's the concentration, the molarity of that solution? We titrate that with 25 milliliters of 0.105 acetic acid. Okay? Now, remember the discussion of the equivalence point, where the hydrogen ions are equal to the hydroxyl ions. When you have an acid that only has one proton to dissociate, right? These other 3 hydrogens cannot be released. This is the only one. One of these for every one of those. Then you have a 1-to-1 stoichiometry, and we can use the expression molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Okay? Now this only works when the same number of hydroxyls for each molecule come off as do the number of hydrogens come off from the acid, when they're equal 1-to-1. That works. So in this case, all you have to do is decide which one's which. Okay, here's the base. So the base is going to be 23.9 milliliters. Molarity of the base is unknown. Volume of the acid is 25.0. And molarity is 0.105 molar. Okay? So let me see. So I don't have to go dig out my calculator. Let me just look up the answer. So if we solve for this one, how do you do that? Algebraically, this stays here, and that term comes over here as a divisor. So this times this divided by that equals that. So when we do that, the molarity of the base then is 0.110 molar. Okay? So that's number 2. Now, number 3 is the last one of our discussion questions. In the titration of a weak acid, the midpoint corresponds to a pH value of 6.1. What are the pKa and the Ka of the weak acid? Now, when it says the midpoint corresponds, what do they mean by that? Let's look at our graph. When we graph this information, the equivalence point is right here in the middle of that steep part. That's where the acid and the base are equal. Hydrogen ions equal to the hydroxyl ions. The midpoint is where only half of the acid has been neutralized, which would be half of that volume. Then when you follow that half up to here, that shows you where, across here, the pKa is located. And that discussion that I give you in the other video goes into more detail. But to answer this question, the pKa is right at that pH that's given to us here, 6.1. So the pKa for this reaction equals 6.1. All right, so the question then is, what's the Ka? Well, if the pKa is equal to the negative log of the Ka, then we take the negative from here and put it over there. Minus 6.1 equals the log of Ka. Now, how do you resolve that? Well, to find this one, you need to put this over here, which makes it the antilog of minus 6.1 equals the Ka. Okay? So how do you do antilog? Well, if you were in school when I was a student, you'd have to look it up in a table. But now calculators will do the antilog, only it may be difficult to find the key. So you look for the one that says 10 to the x. It should be a function key is shift up from the one that says log. So you find the key that says log, and you hit the shift key to get this one, and that's the one you apply to this value, right? Because this is 10 to the minus 6.1 equals the Ka. Okay? So that I don't have to go get my calculator, that should be 8 times 10 to the minus 7. 8 times 10 to the minus 7 equals the Ka. Okay? That's the third question. Now, with that pre-lab discussion, actually it's a discussion question, the pre-labs are next, and you have to do those by yourself. You should, armed with this information, be able to answer those other questions. And if you watch the video, the pre-lab video, you will get a discussion of why the titration that we're going to do gives us the information to determine the Ka for that weak acid. All right. So I'm going to leave that up there, and now we're going to check the pH meter. The pH meter is a device that performs a direct measurement of the acid concentration in solution. The hydrogen ion concentration transformed into pH would be the negative log of the hydrogen ion concentration is the value that shows on the meter. Okay? So, what we're going to need? Well, we're going to need a burette, right? And this is a device for accurately measuring out liquid that is being dispensed. So, as a consequence, it is marked from 0 at the top to 50 at the bottom in milliliters. So each of the markings in between, there are 10 of them, is 1/10 of a milliliter. Okay? So I think I'm going to need some sort of a dark background to read this. Oh, that would work. A white background will work. Okay? So this is our burette, and this is a burette clamp. This is a ring stand, right? So they're all assembled. Hold it in place. You just be sure that it's securely fastened like that. And then you need to tighten the stopcock. Right? You don't have to over tighten it, but tighten it so that it won't leak. There. And it turns smoothly. Now, perpendicular is off. That's where you want it to be to begin with. If you turn it parallel, anything you pour in here is just going to automatically come right out. So that's ready for us. Well, I'm going to fill that in just a minute with the base. but it's set up and ready to go. And let's see, the pH meter is still changing, so we're going to let that soak. And what we're doing is, this is the electrode that actually measures the hydrogen ion concentration in solution. And it's in a standard buffered solution which maintains a pH of 7.0. We'll talk about buffers in the, or have we already talked about buffers? I can't remember whether it was first semester. Anyway, it's in this buffered solution, and then once it stabilizes, we will calibrate the meter for 7.0, and it will be ready to use to measure the changing pH in our reaction vessel. Now, I've got this reaction vessel. Well, this is actually the waste beaker, so any extra stuff goes into this, and our reaction vessel is an equally sized one right here. But it's on a magnetic stirrer. This machine spins a magnet underneath the plate and couples magnetically with this little stir bar, which is coated in Teflon, and it's got a magnet buried in the center of it. So it continuously stirs, and that's like an extra set of hands. I don't have to stir it manually. So we'll turn that off, and this is still clean, so I can do that. And this, of course, is the magnetic stir bar extractor. So if you need to pick something up out of the solution, you do it with this. Okay. This is a volumetric pipette, and we're going to measure out exactly 25 milliliters to within 0.1%, 0.03% tolerance. All right. I'm going to need the pipette bulb as well. All right. We're also going to need 0.1 molar sodium hydroxide. These are all your materials that I'm gathering together. This is where the buffer came from, here. This is your acetic acid. We're going to measure exactly 25 milliliters of this into our reaction vessel, and then we're going to add sodium hydroxide incrementally and watch as the pH change. And the amount of added sodium hydroxide will have a point association with the pH. So you have XY, one's X, one's Y, and they represent a point on a graph. And that's where you get that curve. You draw a smooth curve against the points that you gain from added base versus pH. All right. So, safety concerns. I've got my hands protected. I'm wearing a lab coat. And I have eye protection. And those are all our materials. So we need to go to the procedure. All right. So changes in the procedure. We are going to use 50 milliliters. Well, actually, first thing we have to do is rinse out this burette. We don't want anything in that burette that is not 0.1 molar sodium hydroxide. So what we do is we add some of it to the burette and we rinse it and dispense with it. We just throw it out. Now the method may call for twice, but these are clean burettes, so I'm only going to rinse it once. So we got a closed stopcock. We have our base. And I think for safety, we're going to transfer some of the sodium hydroxide solution into this beaker and dispense it from the beaker. Okay. Now, just to avoid spilling, I'm going to use this funnel. And actually, I'm going to drop it down a little bit so that it's easier for me to reach. There we go. And we only need to put maybe 10 milliliters or so in here. we're not trying to rinse the air in the burette. We're just trying to rinse the surface of the burette. Okay, so how do we do this? Well, if you're wearing a glove and the glove is clean, then you can just cup your hand over the end and tilt and back. It's about 1/3, 2/3. There we go. One more rinse and we should be done. All right. Now let's bring this over here. And let me get one of these paper towels. And just dab up the extra on my glove. There we go. Keep this handy. Now we're going to dispense that volume through the tip and rinse the tip in the process. Okay. What we're going to do, though, we're going to let it all out. Just completely blow through, because we don't want any contaminants left in the line from the top all the way to the end of the tip. So we just let it go. There it is. Hope you can see it. All right. So now we're going to close it. And next, we're going to refill it, this time to the, not to the top, but above the 0 mark. I might have to refill my beaker also. So here we go. Upsy daisy, all the way to the top and beyond. Okay, that's good. Very good. Now, what we want to do is two things. We want to release some of this and bring it down to the 0 mark. So we start on 0. You don't have to start on 0, but it's more convenient. If we start on 0, then we can read the exact amount dispensed directly off of this. If we start anywhere else, then we have to take that difference into account when we determine how much base was actually added. So if we come back down to 0, we can do that. Just read it directly. But in addition, we also want to blow any air out of this tip. See, there might be air. There is air in that tip right now. So we need to get rid of that vapor lock. So we just do a little bit, a little bit. There we go. All right. That was easy. We got rid of that one. So let me go up just a hair, like this. And where's my Chem wipes? Here we go. Chem wipes. And be sure the tip is clean. And now we're going to, with a little help from background here, I'm going to raise up on my tiptoes and find the level. So my eyes are level with the 0. How do I know they're level with the 0? Well, these devices, the volume devices, periodically have the line for the volume mark is all the way around. So what you're looking for is if you can see the other side of the line that is drawn around the glass, then you're not level. If you can only see one line, like I'm looking at right here, now I know I'm level with this position. But I want to be level with this position, so I bring my eye way up here. There it goes. It's level now. And I gradually open the stopcock. Don't want to go too fast. And then when I get close to it, I slow down. There we go. Until I set it right on 0. There. Now it's on 0. And what I also want to do is just dab off any clingers to the tip. Okay. Now when we open the stopcock and deliver some volume, we only get what came out of the burette and not what was clean to the tip. Okay, so I need this one, that one. I'm going to take just a second and check my camera battery so I don't run out in the middle of a procedure. Okay, just to be safe, I'm going to stop the video and change my battery. So I'll be back in a second. All right, let me put this thing back on my head. And position, we should be ready to go with a fresh battery. Now, pH is still changing, so we're gonna let that go and get set up. So this is my reaction vessel, and what I want to do is dispense 25 milliliters of 0.1 molar acetic acid. So I'm going to dispense some acetic acid into this beaker so I don't stick a potentially contaminated pipette into my stock. So I need, here with this, that's enough, quite enough, 0.1 molar acetic acid. Now, I've demonstrated this to you before. This is your pipette bulb. Press this top and squeeze. That gets it ready. And then the S will suck it up. All right, so here we go. We're on our way from misery to happiness. There we go, almost there. Almost, we'll go up past the mark. There we go. And then we'll press the E. And let's see, before we do that, we need to wipe off the tip. Now we're dispensed down to the mark. Same thing, I find the level and release slowly till we hit the mark. I went too far, I think. Yep, went just a little too far. So let's go back up. I have to wipe the tip again. Let's see if I can do this without messing up. Very delicately press the valve. There we go. Now we'll dispense this into our reaction vessel. So rather than hold that valve down, I'm just going to take the bulb off and let gravity do its thing. Here we go. We're getting there. Now I'm going to take a quick look at the method. All right, we've done that. And then we touch the tip to the side. There we go. That's done. I'll rinse that out later. Okay, now the method describes this particular titration by dispensing, to begin with, 2 milliliter portions and then measure the pH. And only when the pH is greater than or equal to 5 By the way, what's going to be our starting pH? Is it going to be greater than 7 or less than 7? Well, we're measuring an acid, aren't we? It'll be less than 7, much less than 7 actually, and as we add base, the pH will start to increase. Okay, so what we have to do now is to standardize they call it calibrate. We're going to calibrate our pH meter. It's still changing a little bit, but if we don't take too long doing this procedure, then the drift should not be a problem. At least I hope it won't be, because this is the only pH electrode that I have. All right, so to calibrate, I touch this cal, and I stir it, and as I stir it, the pH meter recognizes what pH this solution is supposed to be. It's an automatic, and then it calibrates if it can, if there's not too much drift. And it sure is bouncing around. I hope you can see this in the video. It really is taking a while. What it's doing is it takes multiple measurements and averages them. And if the average drifts too much, then it just keeps taking measurements. And that may be what I'm going to be doing for a while. If I stop stirring, I bet it'll settle down. Okay, now it's calibrated at 7, but it's not going to give us a continuous reading until we press this read button. Come on. At least I thought it was. Okay, I think that read button is special. That read button refers to a data logger that can be connected to the pH meter. Has it got a... I don't know where it is, but I think some of these pH meters have a data logger connection. And you push that button and it tells it to read. But we're going to do this manually. I'm just going to look at it and read the value. All right, that's going to have to do, I think. Yeah, we're going to have to go with that. Okay, so now I'm going to remove the waste beaker, and I'm going to put the stir bar. Oop, broken glass, we'll deal with that later. I'm going to put the stir bar in here and start it spinning. Like this, off to one side. There we go. Because this probe is going to go in there as well. So what I need to do is rinse off the probe. We don't want any buffer hanging on it. Okay. There we go. And any big drops can be removed. There we go. And we put this in here. And hopefully it'll sit by itself without too much trouble. I need to be sure the electrode is submerged. Yeah, just barely. That's the problem with using a large beaker. I didn't use an Erlenmeyer flask because we couldn't get the probe in there. We'd have to keep taking it out and putting it back in each time we added something. So now, I think it's better if it stands up. I might have to hold it. There we go. So what's the beginning pH? Let's see, it hasn't stabilized yet. It's close. Let's give it a chance to stabilize. Yeah, it's submerged. That's good. The pH is still changing. Yeah, I would expect a little lower concentration than that. Let me see what this graph looks like. Yeah, it should be a lot lower than that. I'm still dropping. So I'm going to let it sit for just a minute and clean up this glass while I'm waiting. Get my sharps container. Pick up the big pieces first. See if there are any small pieces that I can identify. There's a small one. And that's good. The rest of them I'll wash down the drain. Okay. Yeah, the pH has dropped below 4. I'm looking to see. You know what I'm going to do? I'm going to check it in the buffer again. See, these are the slight changes that can occur in a real-life experiment. I mean, you can read about them, but until you actually try to perform the experiment, you don't realize how many places they can go wrong. You have to always be aware, have expectations, so that you can tell when something is not right. And this pH probe is not responding quickly, so it could be an old probe. Alright, so the data we get might be a little bit off, but I'm trying to teach the principle and hoping that the data will be good. But if you process the data correctly, the answer may not be exactly what we would expect, but it will be acceptable. Okay, I'm going to calibrate it again. These buffers are very stable over long periods of time. So I'd be surprised if the buffer composition itself were the problem. Okay, we got an error. It wasn't stable enough. That was the problem. Well, the problem, and because the pH is so far away from the expected pH, I may have to do this. I may have to do this manually. I may have to actually tell it what pH I'm expecting. Well, it's not going to let me do that. I may have to use a different buffer. Yeah, it's going to keep giving me errors. Maybe I'll shut it off. Try and bring it back on. Let's try that first. In the meantime, I'm going to get another beaker so I can use this one. I just have to rinse it out. Let's try this buffer. Nice green color. So let's rinse the buffer solution off of this one. And try that one. Come on. This is supposed to be a very simple experiment. Things can get complicated really fast. No, it doesn't like that solution either. Okay, here's what I'm going to do. I'm going to turn it off. I'll unplug the electrode. I'm going to unplug the meter. Then I'm going to plug it back in. Put the electrode in first, excuse me. And let it re-find itself. I may have to get a new meter. Let's try the cowl again. While that's happening, I'm going to look for... I got another one in here. I think this is it. Yeah. The only other possibility is that the electrode has finally given up the ghost. And that means I'm in real trouble. we go. Now let's try calibrating it. I think the value was just way too far away from pH 7, and the meter's confused. See, now it found 7. Okay, now let's clean this off and put it back in the solution. Here we go. And see what value we get. Come on. There we go. Yeah, I think ultimately the problem is the electrode. I have another electrode that's just not here with me. I don't want to have to come back and do this all over again. So we're going to do the best we can as soon as I get a reasonably low value. I'm going to try something else while I'm waiting. Let's clean this one out. I think it had acetic acid in it, but I didn't label it, so I don't know for sure. So now I'm going to put acetic acid in here. And we're going to take this out. Rinse it off. Okay, that's not the problem. Okay, just satisfying my mind. Put this back in here. Acetic acid. Okay, so instead of walking back and forth to the board, I'm going to set up a kind of a rudimentary table. Now you shouldn't do this. You should do this in your lab notebook. But I don't have a lab notebook set up. So this is going to be volume of sodium hydroxide, and this will be the pH, and at 0 volume, what is the pH? Well, it keeps changing, but we're going to have to just call the ball and take a value. I'd like to see it get down to 4, if possible. There we go. Yeah, it's submerged, I think. Let me try something. Okay, I'm satisfied. It's getting there. It's a little bit more. I'd like to start at 4. It should have been down around 2.5 actually. But we don't have time to wait. We got to go. Okay, so we're going to take that as our starting point, 4.10, and then we're going to add 2 milliliters of base. So we'll come down to the 2 milliliter mark. There. And let that stabilize. And we'll see what it is. When we get to above 5, we're supposed to 1 milliliter increments until we get to pH 5.5. So that's 4.71. So the next one will be 4 milliliters. Remember, this is the total amount of base dispensed, not the individual volumes, but the total amount. Okay, so we're going to come down to 4. There we go. And that's still stabilizing. That's pretty good. 4.92. We're still not 5, so let's do 6 milliliters. That is 2 more milliliter increment. 6 milliliters. Here we go. Now we're at 5. Just above 5. 5.05. So now we go to 1 milliliter. So we'll go to 7 milliliters total. Will be the next stopping point. Very delicately. There we go. And to get that last bead off of there. There we go. And that's 5.17. Now 8 milliliters. And our next target is 5.5. So let's go down 1 more milliliter to 8. Okay. Watch for mixing. It needs to mix. 5.23. 9 milliliters, which means 1 more mill. Five point 27. 10 milliliters total. Come down to 10. Okay. 5.3. 3. 11 milliliters. Go. 5.3. 9. 5.39. 12 milliliters. Okay. 5.43. 13. 5.4. 8. We're not to 5.5 yet, but we're getting there. This one might be the trick. 13 down to 14. Yeah, 14 milliliters is 5.53. Okay, the method says that after 5.5 we go in 0.5 milliliter additions until a pH reaches 11. So we're going to do a half a mil. So that means we come down 14 and a half. 14.5 milliliters. All right, just need my background. Here we go. 5.58. Then 15. All right. There you go. 5.61. 15 and a half. There you go. 5.65. Not moving as fast as I thought it would. 16 is the next one. We'll stop at 16. Okay. 5.68. 16 and a half. 5.71. This is not looking as pretty as I expect it to be. 17 is the next stop. .74, 17.5. Okay, we'll do 17.5, and then I need to think about this. .78. The thing that puzzles me is if we put 25 milliliters of acetic acid, 0.1 molar acetic acid, and we're titrating with 0.1 molar sodium hydroxide, then the halfway mark would be what? Half of 25 would be 12.5. So 12.5 would be right in here. All right? At between 5.43 and 5.48. And then 25 milliliters would be the equivalence point. And the equivalence point is on the graph. Here we go, right here in the steepest part. Right, we would expect this to be the part we want to really slow down. And we're not even there yet. So that's why I think something is screwy with this data collection. See, it's already drifted. So let's go down to 18. .83, not 15, excuse me, 18. I'm going to pick it up. Let's go straight to 19. .88. Yeah. I think that the electrode is shot. I'm going to keep doing this, but what I may have to do is, if this data turns out to be bad, I'm going to graph it myself. If it turns out to be bad, then I'm going to give you a different set of data to work with. You've seen the procedure, and you've seen what should have happened. You can note that in your report. I'm going to go right on down to 20. Because we should be getting very close to the equivalence point by now. 5.94. Yeah, this thing is not working out at all. So let's see. I would expect to be at 25. Let's go to 22 milliliters. See, now we just barely cracked 6. pH 6, it's still drifting. Still drifting. .1. You know, I got another idea too. While I'm waiting for that to stabilize, I'm going to get a strip of pH paper and see if we're even in the ballpark. If I can remember where I put it. pH paper. Bear with me. I hope I've got some here handy. Nope, that's not it. Let's look in the inner sanctum. pH paper, pH paper. Okay. Might be, here we go. Might be in my other lab coat, but this should work. Yep, this is good. And it's been a little while, so let me check my battery. Bear with me. Looks okay. Put my headgear back on. Okay. Now let's get this pH paper out here. And I'll have to open a new one. How about that? Hope it's still good. Looks kind of old. All right. So let's just do a quick check on this. Okay. That's kind of green. Well, it says it's in the neighborhood of 6, so maybe the pH meter's right. It's doing what I don't expect at 6.33. Alright. Let's go another mill. We're up to 22 mils. We'll go to 23. I wonder if there's something wrong with the solutions. I just made this one fresh, 0.1 molar sodium hydroxide. And this one's been sealed in the bottle. Acetic acid is very, very stable over long periods of time. I still don't trust that electrode. 6.53 and still drifting. 5.4. 5.5. I'm going to call it at 5.6. We're going to go to 24 mils now. Okay. Now it's jumping up. At 24, it's 8 point. Still drifting. Still drifting. We'll call it at 9.0. Next one, I'm just going to give it a half a mil, 24.5, because I think it's acting normal now, which is odd. Yeah, still drifting. We're supposed to go to 11. .64 and 25. There we go. While that's drifting, I'm going to put this meter back in its box. That. 10.05. We're headed for 11. 25.5 mils. Go. 10.27. 26 mils. Okay. So technically we should be past the equivalence point. If these were exactly 0.1 molar base and 0.1 molar acid, we should have exactly the same volume. But then of course, it ain't necessarily so. Come down to 26. Okay. It's slowing down. Appears to be. What's going to happen next is, according to what we would expect in a titration curve, we would expect to see, as we add base, we have a really steep climb in here. We passed that point. Now it's going to kind of come in here and level off. And then the more base you add, the less increase in pH. .65. 26.5 next. All right, let's see here. 26.5. Here we go. .75 and still drifting. We'll give it a chance to slow to a crawl. 10.87. 27 mils is the next stopping point. Let's see here. 27. This should bump it over 11, I would expect. And when we get to that point, we're supposed to switch to 1 mil increments. It's on its way. I'm going to call it at 11. $11.10. 29 milliliters next. Let's see, where are we? Here we go. 29. You have to allow a little time for mixing. $11.2. 30 mils. Let's see here. It's kind of hard to... There we go. There we go. I think we're headed for 11.5, and then we bump it up to 2 milliliter increments after that. $11.38. 31. Let's see. There, I can see it now. Okay. And bam. $11.48. 32 milliliters. This side. And come down to 32. There we go. 11.5 something. Let's watch it for a second. 5.5. Now we can go to 34. Add 2 milliliters. There we go. $11.62. 36 milliliters next. That means add 2 more milliliters. 36. Oops. Can't see the markings, so let's move it up a little bit. There we go. Let's see, 35, 36. 11 point. Seven one. 38 milliliters. Just have to move it. Let's move it down. Now I can see the marking. 38. Bam. Point. Eight one. 40. All right. We're eventually going to get there. Okay, 40. .8. 6. 42. I might have to call it before we get to 12. It's taking a while. Down to 42, 42, 42. There. .9. Let's watch it. 9.3. We might make it on the next one. Let's do 44 milliliters. And down we go. There. Might just make it. I need 700ths added on to the last one. Yeah, I think we're going to make it. 12 pH. Okay. That's the end. So now what do? Well, we turn off the mixer. We rinse off the electrode into the waste beaker. Go. Then we, let's see, let's use the pretty green one. Then we suspend our electrode in the buffer and let it sit there for a few minutes. Okay, now we need to extract our mixing bar, stir bar, magnetic stir bar. Rinse it off. There we go. And we need to rinse out our pipette. There we go. We'll let that drain out, and then we'll hit it one more time. And this is the only cleanup I'm gonna record. The rest of it, you just be sure that all your glassware is clean. You know what went into the burette. It was just base. So really all you have to do is rinse it out really well with distilled water and then put it on the rack to dry. With one caution, and I'll show you what that is right now. When you store one of these, right, this stopcock needs to be loosened. Loosen it up. Why? Because this is plastic and this is glass. The housing is glass. If you put a lot of pressure on that plastic by cinching down this nut, then the plastic will tend to ooze into the openings in the glass. And then when you go back to turn it, it'll stick there. It won't be smooth. So you need to, when you have something like this, Teflon in glass, once you finish rinsing it out, then you need to loosen it completely. So in the process, since this is base, we're going to put it in the waste beaker. So we'll let that drain out. Let's make it easy on ourselves. Clamp it. There we go. Okay, so that's all I'm going to show you. I'm going to put this data on the board and take a picture of it. So, I'll tell you what. I'm going to do it right now. First, I'm going to start this thing rinsing out. Like that. I give it one good rinse, and then I'm going to start putting some data up. Then you won't have to rely on understanding what I was saying when I was calling the pHs. So let's see. I'm going to have to write kind of small, aren't I? 0, 2, and these are in mils. 4, 6, 8, 9, 10. 4, 6, 8, 9, 10, 11, 12, 13, 14. Let's see. This pH could go really close. Like that. I'm going to put these first ones in here. 4.10, 4.71, 4.92, 505. Oh, wait a minute. 6. I left out one. Shoot. There's a 7. There. 5.178. I better do it this way. 5.23. 9. 5.27. 10. 5.33. 11. 5.39. 12. 5.43. 13. 5.48. 14. 5.53. 14 and a half. 5.58. And 15. 5.61. 15.5. 5.65. 16. 5.68. 16 and a half. 5.71. 17. 5.74. And 17 and a half is 5.78. Oh. 17 and a half. Then we go back to 18 here. Move it over here so it would be closer. 18.0 milliliters is what pH? 5.83. 19 is 5.88. 20. 5.94. I should be giving these because we're accurate to 1/10 of a milliliter. There we go. 2022 is next. That's where I got impatient. 6.33, 23, 6.56. All right, it's just come to my attention that the battery cut out before you got to see the entire data table. So I'm going to scan it again. It cut out, we were somewhere in this region. So I finished filling in the table, and I'm giving you a scan, a look at it. Okay. Hopefully you can see everything, and I'll back up and just give you plenty of time to look at the data. Okay. Now that should do it. Now all that's left is for you to plot this data on a graph, view that pre-lab discussion, and that'll show you how to use the graphing results to determine the pKa and then the Ka. And I'm going to do the same thing. I'm going to take this data and see if it's any good. And if I find that it's no good, then I will give you a separate document with a data set that I know is good, so you can have the experience of plotting good data. If this is not good data, and it's 50-50 chance. So, that being said, with whatever data I give you, either this or the other, you should be able to generate a formal report. All right?